Hello, my name is Doug Arey, and I'm the head of the Mountains of Stars program. Thank you for joining this webinar today. Mountains of Stars began as a joint effort between Carthage College and the Appalachian Mountain Club that grew to include Dartmouth College, Smith College, Stony Brook University, and the Alan Alda Center for Communicating Science. In the summers, we have students from these schools who work with us to do programs at Appalachian Mountain Club facilities throughout the Northeast, as well as at libraries, schools, campgrounds, and parks. Our goal in our effort here is to connect you with the very biggest of big pictures and to hopefully change the way that you see your place here on Earth and how we treat everything around us. We've entitled our program, Are We Special? And the Oxford English Dictionary says special is better, greater, or otherwise different. So we're going to come back to this before we're done and ask ourselves, if you take a cosmic perspective, are human beings really better, greater, or actually otherwise different, really, from everything else that is out here? Now, the we that we're talking about is this particular creature. You've probably seen a few of them wandering around here and there. It goes by the designation Homo sapiens sapiens. And interestingly, we're kind of unique. We're the only variety of Homo left on the planet. Over the history of the Earth, there are numerous kinds of Homo that were out there. There were Neanderthals, there were Homo erectus, Homo habilis, all these different kinds of Homo. But Homo sapiens is the last one. And there are very few creatures that can make that claim on this planet. Almost every other one, there are different varieties, but there's only one variety of us. And so in a sense, that makes us kind of special. After all, if Homo sapiens disappeared, everything that looks and behaves like Homo would disappear from the planet. So that's pretty unique. Some other unique things about this creature, it's the only one that fights itself to the death on a regular basis. And it's the only one that does not live in any balance with its environment. Everything else does. It's also a very self-centered creature. To give you an idea of just how self-centered we think we are, we've sent several spacecraft out that have left the solar system and are now traveling among the stars. And given that those spacecraft might be found someday, we put designations on them so that folks would know where they came from. The sort of license plate that you see on the lower right was put on the Pioneer spacecraft, and that sort of star pattern on the left, that tells you how to identify which star the sun is from other stars in the galaxy. A map of the solar system showing which planet launched it. And of the many millions and millions of species that have walked on this planet, the only one that's shown on this plaque is a young adult Caucasian couple. So it's not even representative of the dominant kinds of human beings on the planet or the variety of human beings. It completely misses the varieties of life that are on the planet. Now, later on, we launched Voyager, and Voyager went up with a record, an LP. You can explain to younger folks what an LP is, and if you're a younger person, ask an older person what an LP is. It's a record. It has sound on the back of it. There's information on here as to how to play that sound. Again, the same indicator of which star it launched from. So you might ask, what kind of sounds are on the back of this? Well, there's the sound of wind, there's the sound of water, there is human voice, human music, human language, human song. But guess what? Almost nothing on here would give anyone the indication that there are any other kinds of species that have ever been on this planet. So I'm not a sociologist, I'm a physicist. And so we have to look to others who understand human behavior a little better than I do, for example, to try to see why we look at ourselves that way. And my two favorite experts are Calvin and Hobbes. Calvin and Hobbes say if people sat outside and looked at the stars each night, I bet they'd live differently. Now, I do astronomy. I look out, I see things, I understand the Earth, I understand where we came from, where we fit in, and because of that, I actually do live differently. I treat things differently because of that experience. Now, most people have not had that experience, and so maybe they don't live the same way that I do or live in a different way. I'm hoping that after you've had the experience of listening to this presentation, you actually will live differently because you will have a different viewpoint. Now, we'll start here on Earth. This is a planet you might recognize, of course. And from a human perspective, it is absolutely enormous. If you've had to travel someplace distant, 2 years ago I did some work in South Africa. It takes 2 days to fly to South Africa. That's how big the planet is. And you're probably familiar with the Appalachian Trail, 2,190-mile hike that goes from Georgia to Maine. Well, if you take a look at this map, you realize where Georgia and Maine are, and actually, while it might take you 6 months to walk that distance, it's not that far when you look at the planet as a whole. As a matter of fact, you'd have to do 11 AT hikes to get around the world once. And that doesn't even include the fact that you have to cross a bunch of water. So from a human perspective, the Earth seems very, very large, full of resources, and essentially indestructible. Now, when you leave the Earth and you look back at it, lo and behold, it shrinks very, very quickly. This is a picture taken by a spacecraft that's on its way to Mars. It is a 7-month trip to get to Mars. And yet, only a few hours after launch, it looks back and look at how tiny the Earth and the Moon look, surrounded by a whole lot of nothing. So from a human perspective, it may seem very, very large. But from the perspective of space, it is actually pretty small. Now, if we want to understand human beings and where we fit in, it would help to know where it all came from. So we'll start the story at the beginning, and that's actually a very, very big deal, because in my lifetime, there was still a debate going on as to whether the universe had a beginning or not. And in fact, it did, and we now have a very good age for it, and that is 13.83 billion years. So the universe is 13.83 billion years old. Try to remember that number, roughly 13 billion. It's going to come back to us a little bit later. Now, one of the really unique things about doing astronomy, but actually in observing anything at all, is you don't see anything the way it is, you see it the way it was. As a matter of fact, wherever you're sitting now and you look around the room, you don't see things as they are, you see them a little bit in the past, because it takes time for light to reach you. So if you're looking across your living room right now, and that wall is about 10 feet away, you're actually seeing it about 10 billionths of a second ago, which, as far as you're concerned, is right now, but actually it's a little bit in the past. The thing is, when you look up at night and you see stars, you're actually seeing light that has taken typically a few hundred to a few thousand years to reach you. So those stars are actually a few hundred to a few thousand years older than what you see, because that much time has passed since the light left there. Now, for a star, a few hundred to a few thousand years is really a tiny fraction of their lifetime. And so, yes, everything you see up there really is as it is today. But when you look out farther, you see farther into the past. If you know where to look, you could easily, with your naked eye from a reasonably dark place, pick out the Andromeda Galaxy. That's the next nearest galaxy, and it takes 2.8 million years for that light to reach you. If you look farther out with a small telescope, for example, you can see galaxies that are 50 to 100 million years ago. And if you use the Hubble Space Telescope, of course, it can see very, very far, and it can see billions of years ago. Now, here's a really remarkable thing. If you look out far enough, really, really far, and of course it's very far, so it's very faint, you're looking so far back in time that you're actually able to see the first energy that was able to travel near the beginning of the universe. And we are able to do that, and we can actually map it. So here's a map of the entire sky. Top to bottom is north and south, side to side is east and west. And this is a map of that very first energy, which is the entire contents of the universe shortly after it forms. And you can see that that energy isn't uniform. There are places that have a little bit more, a tiny bit warmer. Those are those sort of orangey and red areas. And some areas that are a tiny bit cooler. Those are those blue areas around there. Now, this energy, as the universe expands and cools, becomes all the stuff in the universe. And from equals mc squared, energy becomes matter. And you would figure that if there are some places in the universe that have a little bit more energy at the beginning, those red splotches, that those would be places where you'd end up with more gas, more atoms, that would become more stars and more galaxies. And the places that were blue would be a little lighter in material, and they'd end up being sort of gaps out in the universe. So let's not look out quite as far. Let's look a little closer. Let's map where all the galaxies are. And you would expect it to be splotchy, just like this pattern is. And lo and behold, that is indeed what you get. So we have a very good understanding of how the universe formed, how that initial energy became all the stuff that you see out there today, and why it has the patterns that it does. It's pretty amazing, but we can figure that out. Now, as the universe expands and cools, and that energy becomes stuff, it's really kind of interesting. It only becomes a few kinds of stuff because it doesn't have a lot of time to do that early on as it's cooling so quickly. 3/4 of everything that gets made is hydrogen. 1/4 of everything that gets made is helium, the next heavier element. A tiny little bit of lithium gets made. And that's it. Those are the only ingredients we have. Now, something that's very important about this that's going to come up and explain how everything works is that hydrogen consists of basically one single proton, one heavy particle with an electron traveling with it. And helium has 4. So the number 4 is very important. The fact that it's got 2 protons, 2 neutrons, 4 heavy particles in it that make up most of an atom of helium. Those 4 particles are going to explain an awful lot about why the universe looks like it does. Now, we're interested in human beings, where we came from, and it's important to note that it takes a lot more than hydrogen, helium, and a little bit of lithium to make people. We need calcium for strong bones and teeth, if you remember the commercial. Oxygen and nitrogen to be able to breathe. You need iron to move that oxygen through your bloodstream. You need sodium and potassium for your nerves. You need everything. A bottle of Centrum says everything from A to zinc, so you need zinc. So you need all the 92 elements that are out in the universe to make a human being. And we don't have them yet. The universe hasn't made them. The universe only has hydrogen, helium, and a bit of lithium. So how does it convert those things into the ingredients that are going to make it possible for human beings to exist? Well, it does that in stars. Stars are giant balls of gas. Gravity pulls gas together. As that ball forms, it's so big and so heavy that at its center, the pressure and temperature go up very, very high. And atoms hit each other and stick. So hydrogen atoms hit each other, and as 4 of them smack into each other, you end up with helium. And in fact, that's how most stars operate. The sun is doing that right now. The other thing is that we also have helium, and that's got 4 particles in it. So we can smack together 1s, helium, hydrogens, and we can smack together 4s, heliums. And so you can combine 1s and 4s, and slowly but surely over the lifetime of the universe, of a star, you start building up these heavier and heavier elements in the core of the star, the heavier ones near the center and the lighter ones as you move farther out. Now, this process is very effective at building up elements up to iron. The thing is, iron is so big and so stable that you don't get any energy if you smack them together to make heavier things. So you need something with a lot more oomph than even the biggest stars. Even very, very big stars can't push iron together and make heavier elements. What does happen, though, is the following. Stars, of course, are born of different sizes. Some of them are small, some of them are big. The very big ones, the ones that happen to be born with a lot of gas, don't live that long. They live on the order of 10 to 100 million years. The smaller stars, stars like the sun, will live upwards of 10 billion years. Those stars, the very big ones, when they end their lives, they explode. And over there you can see what the simulation of one of those explosions look like just after it's happening, just as the star is ripping itself apart. That explosion has so much energy in it that it will smash the ions together, and it produces the remainder of the elements. The other 66 elements all get produced in those explosions. There are also collisions. We have observed with gravitational waves how neutron stars can collide, for example, and those collisions can also produce lots and lots of heavy elements because, of course, there's a tremendous amount of energy released. So we have this process where over millions to billions of years, elements up to iron are bred inside of stars, and then during explosions and collisions, in a matter of a couple of seconds, all the heavy elements get built. So we now know where all of those 92 elements came from. You might recognize this chart as something you might have seen in high school chemistry, but all those elements are produced either during the lifetime of a star or when the star dies. As you can see in the blue color, all the hydrogen, most of the helium, a little bit of the lithium comes from the Big Bang. Every other element here was made during the lifetime of a star or at the death of a star. Now those processes are very, very pretty. The object on your left here is nicknamed the Crab Nebula. The first person who saw it through a telescope thought that the little blurry thing he saw sort of looked like a crab. You can decide what you think it looks like, but it goes by that name. This is the result of a star that exploded, and because it's from an explosion, that cloud of gas that you see contains all of the elements. During the star's life, it bred elements up to iron. When the star exploded, it bred all the other elements. All of them were then expelled out into space. So you can think of that cloud as being a very effective supermarket. Whatever kind of element you want, it's there. It's like going to Amazon or Super Walmart. Whatever you want, you can find it in that cloud. Now, if you remember, only really, really big stars explode. Smaller stars, stars like the sun, don't explode. The sun is never going to explode. Don't worry about that, science fiction. No, sun's never going to explode. But when those stars end their lives, lo and behold, their cores shrink and the outer part of the star does float off into space and gives you an object sort of like the one to your right. This is the result of that kind of process. This one's nicknamed the Helix Nebula, and it's kind of spiral in shape, as you can see. That cloud of gas is also quite dirty, but it's not quite as dirty as the one on the left because this star, of course, did not explode, and so the only elements you find there are elements that are lighter than iron. So you can think of this not so much as a Super Walmart, but more like a Circle K or 7-Eleven or maybe your local Walgreens, in that you can get a lot of very basic things there, but you can't get the complicated ones. The big heavy elements have to come from an exploding star. All of those lighter elements are made in these smaller stars. So here's a really amazing story. Once upon a time, 5 to 8 billion years ago, at least one of these very big stars exploded, and 2 or 3 lighter stars, smaller stars, ended their lives just at the right time in the right place to spew back into space piles and piles of gas that now had all these additional elements in it beyond the hydrogen and helium. Gravity pulled that into a new cloud of gas, like the one you see to the upper right there, and that cloud contains lots of hydrogen and helium, but also has the other 90 elements in it, courtesy of these stars that have died. In that cloud, new stars formed. One of those stars turned out to be the sun, and the debris from forming the sun condensed to form the planets around the sun, including the third rock from the sun, which is us. And rock is actually very important. When planets form, they form into one of 2 broad categories. The ones that have lots of these heavier elements around become rocky planets. And in our solar system, Mercury, Venus, Earth, and Mars are all very rocky planets. Farther out, you end up with gassy planets, where the lighter elements end up being pushed farther out. And in the solar system, we have Jupiter, Saturn, Uranus, and Neptune. And the thing is, you can't live on one of those giant planets. They're made out of gas. If I drop somebody into it, they sink into that gas and get crushed and die. So we can't live on a gassy planet. We need a rocky planet. Now, rock is a very, very interesting thing. Rock is made up primarily of 4 elements: oxygen, silicon, iron, and magnesium. Those make up almost all of the content of the Earth. Remember, all those other things that we see on the surface are just on the surface. The whole big bulk of the Earth are made of those 4 elements. Now, what's unique about those 4 elements is they are all multiples of 4. You can take helium atoms, which remember have 4 particles, and as you add 4 particles to 4 particles to 4 particles to 4 particles, and as all the elements get made, even though we can add 1s and 4s, you end up with the atoms that are multiples of 4 more often than anything else. And so oxygen is 4 times 4. Silicon is 7 times 4. Iron is 14 times 4. So the reason that you have rock, the reason you have all of geology, all of earth science, is actually a result of the fact that stars are better at putting 4s together than anything else. It means that if we were to look anywhere else in the universe and find planets and materials, we're likely to find the two classes. We're likely to find gassy planets made up of those lighter elements, and we're going to find rocky planets with rock that is fundamentally similar to our own, because guess what? Stars make multiples of 4 more than anything else, which means there's going to be lots of silicon and oxygen and magnesium and iron floating around to make rocky planets. Now, if we want to think about life and where life came from, the story goes that we had all of these elements floating in our atmosphere. You had a lot of lightning and ultraviolet. The carbon atoms start gobbling up other kinds of atoms. They make simple organic compounds. The organic compounds become chains, which are proteins. The proteins find a way to reproduce each other. That forms the first kinds of life. And we have those very simple life forms to begin with. Over time, those life forms evolve to be bigger and more complicated life forms until, lo and behold, we show up and we're the latest and greatest and the best that's ever been. Now, if you remember the story of Pinocchio, you realize that my nose is growing because there's a lot of what I just said that isn't entirely true. There are a couple of things that are true. One is we did start with very simple life forms because we only had very simple ingredients. You put these atoms together, you're going to get very basic proteins. You're not going to get very complicated things to start. And human beings actually are a very recent arrival on the Earth. We'll put some numbers to that shortly. So we are a very, very recent thing. The thing is, it was not a simple pathway from the simple life to us. There was a lot of stuff that had to happen, most of it happening from things from space. So let's think about some of those. And we're going to start with a little item that I know is one of your absolute favorites, dessert. Everybody likes dessert. And why do you like dessert so much? Because it's sweet, and sweetness comes from sugar. Actually, sugar is extremely fundamental. Turns out that sugar is the basis of the energy systems of every single living thing on this planet. Everything either eats it or makes it. You eat it. In order for you to continue to function, for you to move around, jump up and down, talk, sing, laugh, everything you do is based on having sugar in your bloodstream. That sugar comes from the foods that you eat. Everything you eat ultimately becomes sugar. Other things on this planet make sugars to power themselves. Bacteria do this. Plants do this. You may be familiar with a very, very important little industry. We take trees, maple trees in particular, and in the spring we drill holes in them. We take the sap out of the trees, we boil it down, and we put it on pancakes. And we like to do that because, of course, maple syrup is sweet. Maple syrup being the absolute ultimate universal food. There isn't anything that doesn't taste better when you involve maple syrup in making it. Trust me, it's fabulous. Now, that process of making sugar is the process of combining carbon dioxide and water. So plants today are taking carbon dioxide out of the air, water out of the ground, combining them and making sugars. Now, look carefully at what it takes to make up a sugar. We have hydrogen. There's lots and lots of hydrogen in the universe. We don't have to make any of that. We've got plenty of hydrogen floating around from the very beginning. Oxygen, I told you before, is 4 times 4. So there's a lot of oxygen in the universe. And guess what? The third thing that we need is carbon, and carbon is 3 times 4. So as stars age and they combine elements to make heavier elements, they actually make more carbon and oxygen than anything else. If you look at the atoms across the entire universe, all 92 different elements appear, tremendous amounts of hydrogen and helium because that was made at the beginning, and then of all the other 90 elements, there's more carbon and oxygen than everything else combined. Carbon and oxygen are extremely common. And since carbon, hydrogen, and oxygen are the most common things out there, lo and behold, sugar becomes the best way to have living things. If you look carefully and you add it up, and I won't ask you to do that, you'd find out that as you make sugar by combining carbon dioxide and water, you have oxygen left over. Some of the very early creatures on Earth, called cyanobacteria, actually were the first ones to combine lots of carbon dioxide and water and to spit out a lot of oxygen, and that changed our atmosphere. You see, oxygen attacks everything, so having oxygen floating around is actually pretty rare. In order to have oxygen in an atmosphere, you need something living to convert that carbon dioxide. When you look at pretty much all other planets, you look at Venus, for example, you look at Mars, for example, their atmospheres are almost all carbon dioxide. Carbon dioxide is going to be the most common kind of planet atmosphere that you would find because carbon and oxygen are so common. But it took those cyanobacteria to convert the atmosphere to oxygen, and without that, you can't exist. Because it's very, very efficient to eat sugar, breathe in oxygen, break the sugar apart, and get lots and lots of energy out of it. This is the reason you do not give children candy bars before bed, right? You do that, they bounce off the walls. There's a tremendous amount of energy available in sugar, but you need oxygen to break it apart. So were it not for that first collection of bacteria to convert our atmosphere from carbon dioxide to oxygen, you wouldn't be here. In fact, all the kind of life you see that eats sugar would not exist. Now, oxygen connects to everything. It binds into rock. Carbon dioxide and extra oxygen get bound into rocks, and that actually changes the characteristics of the rocks. And it's very, very important that this happens because this leads to another step in the process that makes you and me possible. Now, of all those elements that get generated by those exploding stars and collisions, many of those very heavy ones are radioactive. So uranium, for example, is radioactive. That's very important. Those radioactive elements are what keep the core of our planet hot. We have a lot of heat still left in the Earth, and that means a lot of the rock is still melted. It's still molten. It's lava. Because of that, our continents float on top of this molten material, and the temperature at which it melts and the kinds of minerals you get depend on the life forms, because the life forms change the kinds of elements that get bound into that rock. That rock gets sucked back down at these plate boundaries and get remelted into new minerals that come back up underneath the continents. And this is a critical process for keeping life that exists on land, like you and me, possible. Every time it rains, the continents wash away. Erosion would drive away the continents. Over a few 100 million years, the continents would have disappeared, but they're still here because rock keeps getting melted, keeps getting shoved under the continents and pushing the continents back up so that we have land to stand on. And remember that all the life on the planet changes the atmosphere, that changes the composition of the rocks, that makes it possible for this process to go on. Okay, let's look at a couple of more things that contributed to our existence. And we'll start by looking at the giant planet Jupiter. It's the largest planet in the solar system, and it's truly immense. 1,300 Earths would fit inside of Jupiter. Absolutely enormous. It and the other gassy planets, Jupiter, Saturn, Uranus, and Neptune, all have tremendous numbers of moons. As a matter of fact, Jupiter has 79 moons. Saturn has 82. Uranus is 34. Tremendous number of kids. Big, big, big families. Now, Jupiter has 4 moons that are quite large. Io, Europa, Ganymede, and Callisto. They're shown here. And you can actually see them very easily. Any pair of binoculars, if you know to pick out Jupiter in the sky, you can see these 4 little dots traveling along Jupiter. Its other moons are fainter, and you need a bigger telescope to see them. And they are absolutely huge. When you think about that 1,300 Earths would fit inside of Jupiter, you realize that those are pretty big rocks floating around out there. But compared to Jupiter's, you can see they're absolutely tiny. Now, the gassy planets have lots and lots of moons. Let's think about the rocky planets. Mercury has no moons. Venus, no moons. Mars has 2 asteroids that wandered nearby. It has no natural moons. And then there's us. Now, you were brought up thinking that the moon was normal. Sun, moon, stars, of course we have the moon, right? Moon is normal. Guess what? The moon is not normal. We are not normal. We are very, very strange. We have the moon because early on, while the solar system was forming and the Earth was still a molten blob, it got hit by something else within the solar system, something about the size of Mars. And that collision spewed out a whole chunk of material, which cooled off, condensed, and became the moon. That collision, which was, if you wish, sort of a random event, gave us this large moon, and it's enormous, absolutely huge. We're actually a double planet. If we were amateur astronomers on another planet looking at this, we think we're pretty sexy. Hey, have you gone out to see the double planet tonight? It's pretty amazing that we have that. Now, what does that have to do with you and me? One of the biggest effects of the moon is to create large tides. Those tides slosh the water back and forth. So if you go down to the seashore, the fun time to go is at low tide, because in these little tidal pools, which have been isolated because most of the water's been pulled away, you find starfish and sea urchins and sea cucumbers, all sorts of really, really cool things. Now, early on, and in fact for the better part of 4 billion years, all the life on the earth was in the ocean. There was immense amounts of life, but it was all in the water. There was no life on land. Life didn't make it on land until, believe it or not, only about 400 million years ago, which is like 10% of the life of the earth. So a very short period of time. How did it get there? It got there because the moon kept pulling the water away periodically. Every couple of times a day, every time you have a low tide, water disappears. Anything that got stranded out on the rock dies. It needs water and it doesn't make it. But eventually something got stranded up on the rock and it survived and it became you and me. And in fact, it ultimately evolved to become all the life forms that we see up on dry land. So consider the following. If we didn't have the moon, chances are the earth would still have lots of life. Chances are it would all still be in the water. We wouldn't see life up here on land. And we're land creatures, so we need that moon to do that. Reminder, we only have the moon because we had a collision, and those collisions are pretty rare and pretty random. So had we not had that collision, we wouldn't have a big moon, we wouldn't have big tides, and life would still be in the water, and you wouldn't be here. Now, there are a variety of other reasons why we exist. I'm going to go through just one more because there's just so much of this I'm sure you want to listen to at one time. And this is the only chart that we have in the talk, so please survive the graph, just one graph here. This is a chart that shows the history of the Earth from left to right, the beginning of the Earth there at the lower left corner, and current time at the lower right. On the vertical direction, we're charting the number of broad families of life that were on the planet. And you'll see that as the Earth formed shortly thereafter, after it cooled, a whole bunch of life forms showed up, and then all of a sudden 57% of all the life disappears. 57% of it gets killed off. With that gone, new kinds of life show up, and including those bacteria I mentioned before that converted the atmosphere from being predominantly carbon dioxide to being predominantly oxygen. Now, remember, there are lots of other living things on the planet at the time that depended on that carbon dioxide, and without that carbon dioxide, they die off. And in fact, half of all the life on the planet gets killed. Half of everything dies off. Well, in these new circumstances, new kinds of life show up, pretty stable there for quite a while. And then we end up with a period where a lot of lava, as the continents move around, a lot of lava pops up in what we now call Siberia. That puts a lot of sulfur into the atmosphere. It changes the climate, puts a lot of acid out there. And 5/6 of all the life, 84% of all the life, gets wiped out. With them gone and the slate really, really clean, all sorts of new kinds of things show up, and we have the longest period and the greatest growth of life forms that the planet has ever seen until 47% of them get wiped out. And with that gone, we have the fastest rise of new species at any time in the history of the Earth. And lo and behold, we show up. Modern humans, Homo sapiens, have been on the planet 50 to 100,000 years, about 100,000 years. Homo of any kind, anything that looks sort of like us, a couple of million years. This is a 4.5 billion year chart. So you can see that we are a very, very recent addition to the planet. Now, who was it that was here before that 47% wipeout, that was here for such a terribly long time and was very, very successful? It's these guys. That's the age of the dinosaurs. Now, you've been here 100,000 years. They were here 250 million. So who's really more successful? The thing is that they had a bad day. You think you've had a bad day? You went to start the car, you were out of gas, you had to borrow one, you got to work late, your boss was mad at you, you spilled coffee. You think that's a bad day. No, a bad day is when a rock falls out of the sky. This one was between 6 and 10 miles across, smashes into the coast of Mexico, where what we now call the Yucatan, creates a huge crater called Chicxulub that generates a lot of fires, puts a lot of ash in the atmosphere, the planet's temperature changes, and over a span of a few hundred to a few thousand years, you and everything like you gets killed off. Now, while the dinosaurs were here, there were mammals, but they were all small and burrowing, and they had to be because these guys were very hungry. They could run 40 miles an hour, and as you can see, had enormous teeth. They were very hungry. They were the greatest predators the planet's ever seen. So if you happen to have offspring that were a little bit bigger, a little bit taller than average, they got eaten before they could pass their genes on. So mammals stayed very, very small. But once the dinosaurs get wiped out, lo and behold, mammals grow to be bigger. Anything bigger is more efficient, better at feeding itself and surviving, and mammals take over the planet. So even though you might ask somebody, ask a child, what's your favorite animal? Chances are they're going to name a mammal, lions and tigers and bears. But mammals have only dominated the planet for a very recent and short period of time. Dinosaurs dominated for a much longer period of time. The thing is, we've had these 5 huge extinctions. 5 times the planet's basically been wiped of life. That's not the last one. It's going to happen again. Now, we may or may not be hit by another large asteroid. There are astronomers out there looking for them all the time. And there are small asteroids that pass by the Earth periodically that you'll see in the news. But we're out there looking for things, and right now we don't see anything large heading in our way. But, it's always possible. But I can tell you about one extinction that is going to happen, and some of you have probably visited the site where it's going to start. And that's Yellowstone National Park. Yellowstone is a supervolcano. It's an enormous blob of molten rock magma coming up from deep in the earth. And this is a volcano that's a quarter the size of an enormous western state. This is not like Mount St. Helens blowing up in 1980 or Mount Pinatubo or Mount Etna. This is an enormous quarter of a state that is eventually going to blow. Now, it's not going to happen very soon, but over the next 5 to 10,000 years, we're looking at something significant happening. Now, when you realize that, the Romans were only a couple of thousand years ago, a few thousand years in the future isn't that far in terms of human civilization if we don't kill ourselves off before that time. When this goes, it's going to wipe out an awful lot of life on the Earth. It's going to change the entire atmosphere in a way that many, many things are going to die off. Now, you can think of this as being kind of a sad moment, but realize the only reason you're here is because the dinosaurs got wiped out. And the only reason that they were there was because 84% of everything else had gotten wiped out. And the other reason that they were there was that half of everything before them had gotten wiped out. Now, if those things don't get us, the sun will. In roughly 5 billion years, the center of the sun will run out of its core fuel, the core will shrink down, the outer part of the star is going to swell up, and the Earth is going to get burned up in that process. So everything you see around you is going to get vaporized and sent back into space. If you have a chair in the room that you're at, the carbon atoms in that wood are going to get split apart and sent into space. The calcium in my bones will be split apart and sent back into space, wherever my bones have ended up over the next 5 billion years. Every single atom that's around here is going to get broken apart and sent into space. You're now wondering why you're spending the time listening to this very depressing presentation, but again, remember that the only reason you're here is because this happened to at least 2 generations of stars before us. The reason there is calcium to be in your bones is because a prior generation of stars and planets created those. When that star died, its outer portions and whatever planets, life forms, structures, whatever might have been around it got vaporized and sent back into space, and that material condensed to become you and me. The universe is the ultimate recycler. Everything that's here has always been here. It's been rearranged. The particles have been put together in different ways. But every single proton that's here today was there at the very beginning. So you may think you have a certain age, the number you got at your last birthday, but I've got news for you. You and everyone and everything else around you is the same age, 13.8 billion years. The parts that make up your body are 13.8 billion years old. It's hard to envision this, but to realize that everything that's here now originated at the beginning of the universe. It's been rearranged, it's been reconstructed, but everything that's here gets used over and over again. And today it's condensed into your body. And far in the future, it will be elsewhere in space and become something else. Now, we've considered a lot of the processes that have made it possible for humans to be here. And the question is this the only place that there's life in the universe? It's a very important question. And we don't know yet quite what the answer to that is. But you'd say, okay, how likely is it? And there are a few things you need. Well, firstly, you need to have planets. You need to have something that the life can stand on. To have the planets, of course, you need to have enough stars out there to have planets going around them. And you'd want to have enough of the chemistry to make life possible. We need a bunch of all those elements we talked about that make up the life-giving compounds. If you had asked me even 25 years ago, are there planets elsewhere in the universe? I'd have said, well, it's hard to believe that this is the only place that there are planets. There's an awful lot out there, but we don't really know. Well, today we do know. We have a number of different ways of finding planets going around other stars. The most prolific was a spacecraft called Kepler, and what it did is it watched a bunch of stars, and every time a planet in its orbit goes in front of the star gets a little dimmer because a little bit of the light gets blocked. And if that happens over and over and over again, you can identify planets there. So, believe it or not, Kepler found 4,000 of them in a small area of sky. We have a new spacecraft called TESS up there right now that's looking even more precisely, trying to find even smaller planets going around stars. This diagram you see here shows notional ideas of what a few of those first 4,000 planets look like. So we now know that there are planets going around pretty much all kinds of stars. Big stars, little stars, hot stars, cool stars, near stars, far stars. So if you've got stars, chances are those stars have planets. And there are a lot of stars. This image taken by the Hubble Space Telescope is called the Ultra Deep Field. And what you're looking at here are galaxies. We live around the sun. The sun is just one of roughly 500 billion stars within one galaxy, the Milky Way. Each of the smudges you see in this picture, and there are 5,000 of them in this picture, is a galaxy that has somewhere between 50 and 300 billion stars in it. The thing is, you're only looking at about as much sky as your pinky nail at arm's length. So in a tiny area of sky, there are 5,000 galaxies, each with on the order of 100 billion stars. If you move your pinky nail to a different place in space, lo and behold, you'll find another 5,000, then another 5,000, another 5,000. You put it all together, there's something of the order of 1 trillion galaxies in the universe, each with 100 billion stars. And we expect that each of those stars has a couple of planets. So there are an awful lot of planets around an awful lot of stars throughout the entire universe. Now, do they have the chemistry to make life possible? When we see these beautiful pictures of gas clouds up in space, like the one to your left, that's nicknamed the North American Nebula. If you look closely, you might be able to identify the Gulf of Mexico, Florida, the Yucatan, and if you look closely enough, Cape Cod is up there as well. Now, the reason that these things have these shapes is not just because this is where the gas is, but those darker areas are actually clouds of dust that are between us and the gas cloud and just blocking the light from the gas and the stars. That's why you see fewer stars there. Those clouds of dust are mostly made out of carbon compounds, the kinds of things that you need to make life. So floating through our galaxy are these dark clouds. Those clouds have the life-giving compounds that you need to build things that look like you and me. And they're spread throughout the galaxy. If you look to the upper right, you see what the Milky Way looks like if you can get someplace dark. And that big band of dark going through the middle of it is not an absence of stars. That's a big band of this life-containing dust, or life compound containing dust. And if we look at other galaxies, like the one to the lower right, even galaxies elsewhere in the universe have these clouds of dust in them as well. So we're looking at 1 trillion galaxies, each with 100 billion stars. Each of those stars has a handful of planets, and all of it is floating around in space that has all of these life-giving compounds around. So I don't know about you, but it sounds pretty unlikely that this is the only place in the universe where life happened. But what could it look like? When people look for life in the universe, what they're most excited about trying to find is Star Trek. Things that walk on 2 feet, have 2 ears, 2 eyes, a nose, and a mouth, speak English, Romulan, Klingon, or Vulcan. And that depends mostly on the fact that human beings think that we're awfully important. So if we're the most important kind of life here, then of course important kinds of life elsewhere are going to look like us, right? Well, think about the history of the Earth. Modern humans have been here 100,000 years. Human-like things about 2 million years out of a 4.5 billion year history. Think of all the other kinds of life on the planet. We're up here in New England where we have lots and lots of insects. Guess what? Insects do not look like us, and there are way more of them than there are of us. Plant life, grass, trees, lots and lots of plant life. There's way more plant life than there is animal life on the planet, and none of it looks like us. 70% of the planet's covered by water. There are all sorts of sea creatures and water creatures. Here we have some New Hampshire trout that you can see. They don't look like us either. So why is it that if you look for life elsewhere in the universe, you would expect it to look like us? There are hundreds of millions of different species that have been on this planet, and precisely one of them looks like us. There are so many ways to build life. Lo and behold, if you found it on another planet, having something that looks like us, from my perspective, is pretty unlikely. Now, if you go back even a couple of hundred years, people were pretty connected to things in space and looking up at the sky. But most folks today aren't, and there are a number of reasons for that. But one of the biggest reasons that people aren't connected to it is light pollution. And light pollution is actually a much bigger problem than losing the night sky. It actually has very significant health effects. If you live in a light polluted area, you're at higher risk of getting breast or prostate cancer. It contributes to obesity and diabetes. So having extra light is not a matter of making it healthier, it actually makes it less healthy. Lights that are too bright and create glare actually make streets less safe. It has effects on plants and animals. Pollination is down up to 62% in light polluted areas because the insects and birds that carry pollen and seeds from one plant to another, they don't see those plants the way they should because of the artificial light. Over 1 billion birds die each year trying to migrate because they get trapped in the lights of cities. So it has tremendous effects on the natural environment and on your personal environment beyond just losing the night sky. Now, this image of the United States taken from space shows a lot of light that is streaming upward. None of this light is actually producing anything useful on the ground because you can see it from the satellite. This is light that's going straight up. What's very unfortunate about this, beyond the fact that it's a waste of light, is that it's also a waste of energy. To keep a 100-watt bulb lit for a year, one has to burn 2,000 pounds of coal in a power plant. So think about how many 100-watt bulbs all this light represents. Multiply each of those by 2,000 pounds of coal, and think about all the pollution that's generated by burning that coal. And that doesn't include the pollution from the diesel engines on the trains that move the coal, or the work that went into mining the coal and processing the coal. So this is a tremendous environmental effect beyond the direct effects of the light, but producing all that electricity that's making light that we're not even using. Here's what the light pollution map looks like for southern New England. Many of you are in the Boston area or the New York or southern Connecticut area, and you can see all of these very, very bright areas, and indeed how far out you have to go into the ocean before that light actually dims very much. Now, this is a problem that's getting worse. This is satellite data from April of 2012 and gives you an idea of, throughout New England. You can see Montreal up near the top there, Boston to the lower right. The sad thing is, well, this is what it looked like in 2012. This is what it looked like in 2018. In a span of 6 years, a tremendous amount of growth in light. And this happened for a number of reasons. One is general growth. More people, more businesses, more houses, bigger towns. So that's part of that growth. But a second part of it is the introduction of LED lighting. Now, that should have been a good thing. LEDs are a wonderful technology. They're very inexpensive. They use very little electricity. They put light mostly downward, in principle, a good thing. But the problem is because they are so cheap and use so little electricity, when people switch to them, they figure if light is good, more light must be better. So the fixtures that go in are too big, too bright, and too blue. And the problem has grown and will continue to grow and get worse and worse and worse with time. This is a projection of what it will look like by 2025. This was put together in 2001, and I think it might be even worse as we move forward through this decade. Now, solving this takes two components. One is putting in lights that are the better color. So this is the same intersection with these very bright, very blue LED fixtures that I'm sure you're familiar with. And you can see there's a lot of glare. There's way too much light. There's light streaming into households here. It's not a very good source of light at all in this neighborhood. In this case, they were able to get those lights changed to something called PC amber, and you'll notice the glare is much reduced, the lighting is much more uniform, and far less glare is being created. It is a much, much better fixture. And all fixtures should have shields on them. This particular parking lot, and this is the same parking lot in the upper and lower pictures here, in the upper picture there were no shields on the light. Below that, shields were put on, smaller bulbs are being used. The amount of light on the parking lot is actually the same or perhaps even a bit more, but you'll notice that there's no light spilling off into areas where it's not needed. There's no light streaming into homes. There's no glare produced. So putting shields on lights is a very important component of putting light where we need it, allowing us to use smaller bulbs. Now, there are programs to track this. One that I invite you to participate in is called Globe at Night. And there's an app for that. This is a citizen science program to track what is happening with lighting. You can contribute to it, and before our talk is over today, I will give you links to all of this information. But it's a very important way to be tracking what is happening with light pollution and reducing its impacts. Last summer, the Washington Post published an article on the loss of night and included this figure, which shows the places in the United States that are still truly dark. Most of them are out west in areas that are pretty much inaccessible, high mountain areas, desert areas, places you can't really get to. You'll notice that in the Northeast, there's only one area. In fact, in the eastern two-thirds of the country, there's only one substantial area that's still dark, and it's in northern Maine. And it surrounds the Appalachian Mountain Club lands up around east of Moosehead Lake and up towards Baxter. We are in the process of working with the International Dark Sky Association to protect that region. And in fact, the sky there is shown in the upper left here. We were trying to make that an international dark sky reserve. It will be only the second in the United States, the 17th in the world. It requires that we get all the surrounding towns and businesses to change their lighting and to put in lighting ordinances so that that sky, which is dark today, remains dark well into the future. Now, we started this discussion asking whether we are special. Are we deserving of more rights and privileges and use of resources because of all the unique things that made us possible? I mean, think of all the things that had to happen. The right kinds of stars had to live and die in the right place. We needed the right mixture of chemistry. We needed bacteria to give us an oxygen atmosphere. We need the right amount of tectonics from radioactivity. We needed a moon we shouldn't have had. All these things had to happen to make us possible. And that's making you feel pretty special. I mean, you think you tweak any of that and lo and behold, we don't show up. The thing is, he can make this claim too. There's only one kind of moose on the planet. He's the last of his kind. He metabolizes sugar. He prefers to be a vegetarian, of course. He's a large mammal, only here because the dinosaurs disappeared. And the truth of the matter is, even the plant life around him can claim that it's special because, lo and behold, that same cosmic history made it possible as well. If you talk to people, they'll tell you that they have this sense that humans are above everything and that all the other life forms on the planet, that there's a hierarchy. I ask that you question that idea and think about the fact that the cosmic history that made us possible also made everything here possible. If anything changed the slightest bit in the history of the universe, lo and behold, everything would change. The life forms here affect the rocks, which affects the formation of the continents, which affects the flow of the water, which affects the kind of life forms, which affect the atmosphere, which affects the rock, which affects the continents. Everything is tied together. Jonas Salk, who invented the polio vaccine, made a very important observation. He said, if you remove all the insects from the earth, in 50 years, all the other life forms end. If you remove the humans from the earth, in 50 years, all the other life forms will flourish. And we need to recognize the impact that we have on everything on this planet. Daniel Goleman's written a whole series of very well-known books. About 2 years ago, he published one called Ecological Intelligence, and he points out that no matter how green you are, no matter how seriously you take this, you're still going to have impacts on things. Know what they are, find a way to do it better, and most importantly, share it. I recommend publications by a number of folks, some excellent books, and on the website link that I'll give you later are references to all of this that you too can learn way more about how this process works and what we can do about it. And there are things that we can actively do about it. We need houses, we need places to live, but when we build them, we have to do them in a way that doesn't impact the environment. Building a neighborhood such as the one shown here has completely broken the environment. No animal can get from one side to the other. We're not considering at all our impact on the environment when we build things. Our food, we waste a tremendous amount of food. And we don't have to do that. You can actually clean your plate. Food that's wasted is not just the food that gets wasted, but the fact that there was land that had to be cleared, water, pesticides, fertilizer, diesel trains to move it, electricity for refrigeration. There's a tremendous amount of waste that goes into overproducing food that we don't eat and don't use. And speaking of waste, we produce a lot of it. You can look at the products that you buy, you can look at the products that your company makes and ask why we have to use so much packaging and waste so much materials to produce the goods and services that we actually use. And our human conflicts, when we have conflicts, and we will always have conflicts, the only thing we concern ourselves about is what happens to the humans. How many people are injured or killed, how many buildings are destroyed. We don't consider the environmental damage of the conflicts that we have with each other. You vote. You can vote on the basis of just what's good for me, what's good for humans, or you can have a cosmic approach and think of what's good for everyone and everything. And it's very important that you communicate these ideas to others. I'm sure you'll be at a dinner party sometime soon. You'll be talking to friends. It's your opportunity to tell them about what you've learned here and suggest that they too can make changes in what they do. Look at what your company does. Find a way to do it better. Look at the lighting at your house. Find a way to do it better. Look at the products that you buy. Find a way to do it better. And share that with others, because only if many people make the changes will we actually be able to improve things here on Earth. I truly believe that Calvin and Hobbes are right. If everybody looked up every day and saw this and realized what they're looking at, realized that there are 1 trillion galaxies, hundreds of billions of stars in each galaxy, planets around each of those stars, that what we have here, yes, is special because this is the one that we have, and change the way that we treat it. Thank you for your time. There are numerous organizations that have supported the work that we do. I hope that you will support them and take advantage of what they offer. I also ask you to help to contribute to the work that we are doing. We have a GoFundMe campaign that you can contribute to that helps support the students that work on our program throughout the summers. And you can get more information about that and everything that we offer through our Facebook page and our website. On our website, you can find copies of all of our presentation materials, links to all the organizations I mentioned, the books that I showed, information about dark sky preservation, videos from top astronomers and naturalists, recent reports and documents, all sorts of information that you can take advantage of. And feel free to get a hold of me. I'd be very happy to give presentations or workshops for anyone you work with, for municipalities, companies, schools, libraries. Thank you very much for your time, and have a good day.